Let's implement the linearly separable support vector machines. Many programming languages, including Python, have built-in libraries because this is a pretty standard classifier. There are many different implementations. I'm going to use the sklearn SVM library. It's not the only one, but it is one that I've used before and I tend to like, so it's a pretty easy library to use. I'm going to bring in NumPy and, of course, matplotlib, because we're going to do some plotting of the data. So this is going to be our SVM library here. In particular, we're going to use SVC, which is going to be the optimization for the quadratic programming for the linearly separable SVM. Synthetic data, again, 20 data points, generate a bunch of coordinates. Notice here I'm generating strictly positive. I'm using rand, 20 of them in two-dimensional space so we can visualize everything. I'm going to make so this is the positive class. The negative class is just negative. And the reason I'm doing this is that I'm assuming that the data is, in fact, separable. It's not always going to be that. We'll deal with that when we do non-separable linear SVMs. And so I'm going to have these two clusters as we did before with LDA. I've got my labels, positive and negative. By the way, notice that it's positive and negative because that's what the cosine told us they needed to be, not 1 and 0. So I've got my labels 1 and -1. I'm going to build my data matrix. I've got it's going to be now 2n, 40 by 2. The first coordinate, the second coordinate for the first class, and then the second class. And then I've got my positive and my negative labels all stretched out. So everything's in one matrix, the labeled training data. All right, let's do some support vector machines. Here it is. SVC, that's the support vector machine. There's a parameter here called C. We'll come back to that later on. And there's something here called a kernel, which is linear. This is eventually where we're going to introduce nonlinearities. But for now, we're assuming a linear classifier, so we put linear here. And I'm going to fit the data to Y. The ravel here is just to make sure that the data has been stripped out into one contiguous array. And this will do, of course, the quadratic programming, which will find the separating surface parameterized by W, a line, B, an intercept, and then I can pull those out of the resulting CLF classifier, which is the coefficient. The subscript 0 is to grab the actual coefficients, and this is my intercept. I'm just going to go ahead and print these out so I can see them. And now I just want to be able to visualize everything. So this was the classifier up here. I'm going to define the boundary because I want to look at that boundary. And the way I'm going to do that is I'm going to enumerate all possible x values and then evaluate what the line is for all those x values so I can simply plot them. Now, be very careful here. Remember, as with total least squares, the W is not the separating surface. It is perpendicular to the separating surface. So when I go to evaluate what y is, it's not y equals mx plus b. It's y is equal to the 0th component minus the 0th component over the first component times the x minus the intercept over w sub 1. And all I've done is taken this equation of the line right here, which was our parameterization, and reformulated it so that x2 is the vertical dimension is equal to something, slope, times the x1 plus beta. And you should be able to see how I've rewritten this equation to give rise to that equation right here. So I can just plot the separating surface from the intercept and the normal vector to the line. Now I'm going to go ahead and just do some plotting. And here it is. Red is class 1. That's strictly positive. Blue is class 2. That's strictly negative. And the line that you see here is the separating surface, which seems to have done the right job. And in fact, it also looks, at least intuitively, that I did, in fact, maximize the margin. Because you can imagine taking this line here, and I could still have separated it with rotating it. But if I rotate it in this direction, I'd be really close to that red line. And if I rotate in the other direction, a red dot, if I rotate in the other direction, I'd be close to that blue dot. And you can see that it's very nicely sort of split that difference, maximizing the margin. Even though there was some wiggle room in there, it didn't just pick some arbitrary orientation. Now, the other nice things you can do with this SVM is that you can assign probabilities or at least weights of confidence to the classification. Intuitively, what is that? Well, the closer you are to the margin, perhaps the less certain you are. And the further that you get from the margin, perhaps the more certain you are. I'm not going to go through this code, but you can look at it at your own time. This is just computing that weight as a function of the distance from the margin. And let's just go see what that looks like. So here again is the same thing. I've got my red points in one quadrant, my blue points in the other quadrant. I have my separating surface here, and I've color-coded with increasing hue, the red and the blue, where the deeper the red and the deeper the blue, the more confident I am because they are far, far away from the separating surface. So this is just a way of visualizing your confidence, where obviously if something is very, very close, maybe you're a little bit less confident in the classification. All right, now, this is actually, despite all the work that we had to go through to get to this, not a very useful classifier. Why? Let's go back to that quadratic programming. The quadratic programming said, maximize the margin, the separation of the two classes, subject to a constraint. And the constraint was that everything with a class value of 1 should have a dot product that is greater than 1. Everything with a class label of -1 should have a dot product that is less than 1. But what it didn't say is, well, what happens if just one point is misclassified in either direction? There is no satisfying that quadratic program. And now you're out of luck. So the linearly separable SVMs only work when your data is actually linearly separable. And it will not work when the data is not separable. The quadratic program will simply say, I cannot satisfy all of these constraints for every single data point subject to maximizing the margin. And that's where what we will talk about next comes in, the non-separable linear SVMs.